So what I want to do is I want to practice with you a couple problems in terms of optimization, and then I'll go through last semester's test and talk about the things that I would expect and want you to get out of a problem as we work through it. So this one right now is going to be trying to optimize the shape or the dimensions of a rectangle that fits inside of this parabola. So let's think about the four elements that I'm going to be looking for when I grade your papers. Picture, I might even give you a little bit of the picture, but what you should be doing with that picture is labeling it. So for instance, this is going to be some point X and Y. Because this goes through the x-axis and it's symmetric, let me just do this. There's a little subtlety about this problem in terms of labeling the sides. This side would have what for a height? Yeah, it has to have y for a height. The length, the total length of this side, you have x here to get to here, but you also have negative x here, or a distance of x. Overall, the total length of that side is 2x. And that's something that's very easy to lose track of, so I want to take care of it right away. Do you remember the four little steps that I broke this type of problem down into? It was picture, function, interval, and analysis, right? So let's take a moment and think a little bit further. Where is this graph going to cross or touch the x-axis? Well, we'll come back to that when we do the interval. Right now, as far as the function is concerned, I want to maximize the area of this rectangle. So let's think here. Let's think in big terms. Area of a rectangle. We don't have to try and write it all in terms of one variable just yet. Let's just start out with big terms, big ideas. How do you find the area of a rectangle? Length times width. And I ran out of room there a little bit, my bad. But length times width. All right, so let's call this the length. What's the length going to be? 2x. And then the width has to be the other dimension, so that's going to be a y. So we're okay there. But when you're coming up with your function, what's the one thing that you really need to do with your function? What does it have to, what properties does it have to have? Yeah, it has to be of one variable. And right now I've got an x and a y. Calc 1, I like to say sometimes, is calculus of one variable. Not just Calc 1, first semester, but it's calculus of one variable. So how can I write this depending on one variable? Yeah, let's put in what y is. Y is 4 minus x squared. So this is 2x times 4 minus x squared. If you'd like, you can distribute that. 8x minus 2x cubed. But the important thing is that now I can write that as a of x. It just depends on one variable. Wonderful. Interval. Well, we can't make this rectangle as big as we want, and that's why I was asking you about, well, you know, what's the point at which this graph crosses the x-axis? Where does it actually touch the x-axis? 2. Thank you. Why 2? Well, if you solved, you get 0 is where it crosses the x-axis. That is, y equals 0 equals 4 minus x squared, or x squared equals 4, x equals plus or minus 2. And that makes sense, right? You have 2, 0, and negative 2, 0. But x itself is going to be the distance from the y-axis to whatever point we have here. And the farthest I can go is 2. Now there's a little bit of a trade-off here between making it wider and making it shorter. So we want to figure out, well, where's the best place to maximize this area in terms of that trade-off? And you can kind of see it this way, depending on where you put that value of x. Now this isn't the exact right parabola, but it's giving you the same idea. It's a little bit of a trade-off. So let's figure out which one works. Now we haven't figured out our interval yet. Our interval, well, we can't let x be 0 because then we'd have something that's just really tall with no width. On the other hand, we can go all the way out to 2, but does it make sense for x to equal 2? Can we actually have a rectangle if I take this point all the way out to 2? It's going to get really, really short, and eventually at x equal 2 it's going to disappear. So the interval you should be working with is 0 to 2. Okay, looks good there. Picture, function, interval. What's the last step here? Analysis. So let's look at the analysis part. As far as the analysis, I've said it before, we've only got one hammer, so everything looks like a nail. What's our hammer in this kind of a problem? Derivative, yeah. You should probably be taking derivative on most, if not all, of your problems. So right now, derivative, that's pretty easy. This is just a nice cubic function. What's the derivative of a? Awesome, thank you. 8 minus 6x squared. Nice. So that's the derivative. What am I going to do with the derivative, though? How does that help me? What does the derivative tell me? Solve for x where? Ah, so equals 0. When I set the derivative equals 0, I can find the critical points. The points of interest that might be a minimum, might be a maximum, might be an inflection point. We don't know. But let me move the 6x squared to the right-hand side. That way I get rid of this negative. 8 equals 6x squared. Changes sides. It changes signs. Divide both sides by 6. And then that's going to simplify down to 4/3. And finally, I'll take the square root on both sides. There's one thing you should be careful about, and that is taking the plus or minus. Although, in this problem, if you forgot the negative, you kind of get a pass because the negative's not in this interval. So, all right. So we're just going to let x equal square root of 3 over, or square root of 4 over 3. Now I know that I can simplify the numerator as 2 over the square root of 3, but it's okay. I'm not really worried about that. That's kind of an algebra problem. Let's look at what that gives us. Let's make ourselves our usual little table. X, A prime, square root of 4/3. And another one here. So I know that the derivative is 0 right there. But how about to the left of it? How about to the right of it? I need some test points. So let's see. 2 divided by square root of 3. That's going to be a little bit more than 1, I believe. Let's just check that out. Square root of 4 divided by 3. Yeah, about 1.15. So as far as some test points are concerned, I guess I could use x equal 1 as a test point and x equal 1.5 as a test point. Let me remind you how to do these kinds of things on your graphing calculator. So I'm just going to pull up my graphing calculator software. It takes a second or two to open. All right. Let's put in our, row ops, good stuff, isn't it? That's from my college algebra class. So let's see, we want to put in our derivative. That's going to be 8 minus 6 x squared. Let's double check our window settings. You want independent set to ask, dependent set to auto. That way when you go to your table function, you can type in whatever values of x you want. Now I've got some old values there, so I'll delete those. And I'm going to type in values of 1 and 1.5. What information am I getting out of this that I need?
Positive and negative?
Yep, positive and negative. That's really all that I need here. This one's positive, this one's negative. Thank you, Christian. John, what's that telling me about my function that I need to know? What's the function doing to the left of root 4/3 based on the derivative here? Yeah, it's increasing. Perfect, that is decreasing. So what's that say about this point? If it's increasing then decreasing, what's happening there? What can you tell me about this point? It's a maximum point, right? If it's increasing then starts decreasing, in between you had to hit a maximum point. So this is a maximum. Maximum. Great. Now I guess it depends on what exactly they're asking. You could be asked for the dimensions. If you're asked to find the dimensions of this, then we need two things. The length. Length is equal to 2x, so 2 times the square root of 4/3, and then the width, which is going to be y equals 4 minus x squared. So if I put in that value of x, it's going to be 4 minus square root of 4/3 squared. 4 minus 4/3, let's see, that's going to be 4 minus, or how about 12/3 minus 4/3 is going to be 8/3. So the dimensions would be overall 2 times the square root of 4/3 by 8/3. That would be your overall dimensions. Yay. Nice. There's one more comment I'd like to make about this right here. What we did in order to deduce that this is a maximum is that we said, all right, well, it goes from increasing to decreasing after you pass through this critical point. That's great. That's the first derivative test. You could also decide things based on the second derivative test. So what's a second derivative test? Concave up and concave down. So what I'm going to need is a double prime of x. So what's the second derivative of this function? Minus 12x. And if I plug in my point here, square root of 4 over 3, let's see, square root of 4 over 3 equals minus 12 times square root of 4 over 3. I don't necessarily need to calculate what this is. I do know that it's less than 0. So if it's less than 0, what is the shape of the function near that point? Concave down. So you have a concave down shape at a critical point. If you have a concave down shape at a critical point, then that critical point must be a maximum. So that's a different way to prove that your answer actually is a maximum as opposed to a minimum or inflection point. So you've got the first derivative test, what we did here. It went from positive to negative. And you got the second derivative test down here. You don't have to do them both. It's nice to see one of them. Okay.
For this, weren't we looking for
Oh, is it the area? Well, these are dimensions that maximize the area. So I guess it depends on the problem. Let me take a look here. Yeah, actually this one came from an old exam, and it said find the dimensions. So you'd want the x and the y.
Got it. So we just use the area to find the function.
Yes. Yeah, area is what gave us a function to maximize. Nice. Okay, let's do another one. So again, we're going to go back to problem on last summer's exam. So an anonymous, handsome athletic mathematician. Wait a minute, I need to update this a little bit, even though it's still anonymous. There we go. Is gonna is gonna bottle some homebrew. Now, if you're gonna bottle your homebrew, maybe put it in a can. It'd be nice if that can was environmentally friendly. That is, you build it with the least amount of aluminum that you would possibly need. Now, how are we going to do that? Well, okay, we're going to have to think about that a little bit. Really, what we need to do is we need to minimize the surface area of this can. At the same time that can needs to contain about 23 cubic inches of volume. So, there's our picture. Yay. Not much of a picture. We should probably add a few things to this, right? So what could I add? Well, I could add a radius. Put in an R here. And let's see. So there's an R. And then what other dimension might be nice to have here? Yeah, the height. So, okay. Beautiful picture. 2 points for the picture. Let's keep going. There's not much else we can do. What else would I need to put in here? What's the next step? Picture, function. Now, the important thing with the function, and it's kind of what we did with the last one, I didn't start out trying to swing for a home run right away. I didn't try and get this complete form right away. What did I do? I started out with something pretty simple. I said it was length times width. If you're thinking about the dimensions of this can, then, okay. Well, the aluminum you need to construct the can be broken up into two parts, right? What would you call this stuff right here? The ends.
Oh.
The lids, right? Or the top and bottom. So the surface area is going to equal the top plus the bottom plus what else? Is that it? Is that all the surface area we need? Yeah, area of the sides, right? Okay. Well, that's not so bad. What's the area of one of these lids? Either the top or the bottom, doesn't matter. Yeah, so the area of one of them is going to be pi r squared, and we've got two of them, so let's put in a 2 pi r squared. Now, as far as the area of the sides is concerned, there's a little trick that we can pull in order to try and roughly estimate the area of the sides. And let me try and help you with it this way. Suppose that this is my can. I'm trying to figure out the area of the sides, and I'm looking at that, and boy, it just doesn't make too much sense. What if I cut this straight down the seam and unfolded it? What's the shape that I've got here? The rectangle. All right, so this is just going to be the area of a rectangle. Area of a rectangle. And it's the rectangle that I used to create this. Do I have this depending on one variable yet?
No.
No. But we'll keep working on it. All right. So the 2 pi r squared, I'm going to leave that alone for the moment. 2 pi r squared. Area of the rectangle. Well, how do you find the area of the rectangle? Yeah, length times width. All right, that's good. And I know one of those dimensions, right? One of those dimensions is just h. So something times h. But I need to know the other dimension. Now that other dimension, that's just going to be the length of the top, right? The length around the top, to be more specific. So how would I find the length of this circumference? 2 pi r. It's a circle, right? The area of that is going to be 2 pi r. Oh, we're getting closer here. But I need to get rid of the r. Excuse me, not the r, but the h. So I want this to depend on just one variable. There's one other little detail that we haven't used yet, and that is the volume of this is going to be 23 cubic inches. What's the volume of a can? Well, in a sense, it's kind of like the volume of a rectangle, or a rectangular solid, I should say. You're going to take the area of the base times the height. So the volume here is going to be pi r squared times h. Okay. So what I can do then is say, all right, I know what my volume is. That's 23 equals pi r squared h. Does that help me at all? Sort of. Well, remember, I wanted to get rid of the h here, right? Looking back here, does this help me at all?
You can set that equation into h and plug it into.
Perfect. Thank you. 23 divided by pi r squared equals h. And now I can take that and plug it in over here. And finally, after a lot of work, now we have something that depends on just one variable. So it's going to be S of r equals 2 pi r squared plus 2 pi r times 23 over r squared, like that.
I think you need a pi.
Yeah, I do need a pi. Let's clean this up a little bit. One of the r's is going to cancel. The 2 times the 23 is going to give me 46, and the pi is going to cancel. So that'll cancel. Thank you for that, Ethan. Then one of the r's is going to cancel. So that'll cancel one of those. I'll be left with 2 pi r squared plus 46 over r. And as far as differentiating this is concerned, I might want to rewrite that one more time. Any suggestions as to what I could rewrite 46 over r as? Yeah, 46r to the negative first power. Whew. So 2 points for your picture, probably 4 points for your function here, right? Because that was a lot of work to get that function correct. Let's not forget the interval. R is your radius. What's the smallest that I could use for my radius? What's the smallest that would actually make sense? Which one?
0.1.
How about 0 with a parenthesis? What's the parenthesis mean? It can't be 0. It has to be something even marginally bigger than 0. Is there any natural limit? Could I make this radius as big as I want?
No.
I could. At some point, it's going to get really impractical to have it like a mile wide and a millimeter tall, but there's no real theoretical limit as to where you'd put that. I'm sure there's some practical limits. So 0 to infinity. Okay, at least we won't spend time looking for something, that's negative. Picture, function, interval, last step. Analysis. All right, let's take out our only hammer. S prime of r. That's going to be 4 pi r. Then what?
Negative minus 46 r to the negative second.
Yep, minus 46 r to the negative second. Good. Keegan, what do I do there? Now that I got the derivative, that's great. Now what?
You do the table?
I will get to the table, but there's something I'm going to need before I go to the table. What would that be? Yeah, I need to know where it's actually equal to 0, right? I need to find the critical points, and then we'll go to the table. So we will take your suggestion. Thank you. Now, as far as this is concerned, I guess what I would do is I would get rid of the negative exponent. That's really 46 over r squared. And to get rid of the negative exponent, I can multiply both sides by r squared. R squared times 0 is still going to be a 0. R squared times 46 over r squared is going to see that r squared cancel. So just going to be 46. And then r squared times this is going to give me 4 pi r cubed.
Question.
Yes?
I'm being a bit lazy right now, but would it be the same if we were to just take 4 pi r equals 46 over r squared?
Yeah, you'd eventually do the same thing. You'd eventually going to multiply both sides by r squared to get rid of the, yeah.
Less work.
It's a little bit more direct, but if moving this to the other side and then clearing out the fractions works for you better, go for it. Christian?
Would it be easier if we did the second derivative test on this one?
We'll find out. But first we got to find out where this is actually equal to 0. So we get r cubed. Let's see. We'll do 4 pi r cubed equals 46. R cubed equals 46 over 4 pi. And then, let's see. Let's simplify that a little bit. It's going to be 23 over 2 pi. And finally, I want the cube root of that. R equals the cube root of 23 over 2 pi. So that's going to be the radius. Let's calculate that on our calculator. I do like your idea. What are we looking to try and do here? Are we trying to find a maximum or are we trying to find a minimum? Find a maximum, or we're trying to do what with the amount of aluminum we use here? We want to minimize it, right? So we're looking for a minimum. So this is our critical point. Let's just do the second derivative test. I think the second derivative test should be pretty easy from here. Let's see. So let's calculate the second derivative. S double prime of r is going to be 4 pi plus 92 over, or 92r to the negative third. I don't think I really need a calculator here. S double prime of cube root of 23 over 2 pi. Well, 4 pi has to be positive, right? 92 divided by some positive number is still going to be positive. So that has to be greater than 0. If it's greater than 0, what shape does my function have at this critical point? If it's greater than 0, it has a concave up shape. So that critical point has to be a minimum. Nice. Nice. So that critical point's a minimum. We still need to find the dimensions of our can, although we do know the radius. Most places aren't probably going to deal with the radius. They might deal with the diameter, which is twice the radius. Let's figure out the dimensions of this can. And let's do it on our calculator. Because when we do it on our calculator, it reveals something that I didn't realize until I first calculated it years ago when I first solved this kind of problem. So let's take the cube root. So go to the math menu. Option 4 is the cube root. I want the cube root of 23. Let's see, I'm going to do it this way. A little fanciness here for you. If you hit the alpha key, then the y equals key, you can do a nice up and down fraction. Let's do 23 divided by 2 pi. And I'm going to store that in x. That's my radius. So about 1.54. Okay. Now that means my diameter is 2 times that, so 2x. There's my diameter. So the diameter equals 2 times r, or in this case about 3.08. How am I going to figure out the height? How do you figure out the height? You can take your radius and plug it back into this thing, right? 23 divided by pi r squared. And I'll give you a second to plug that in before I do it, or at least before I reveal the answer. So I'm going to do the same thing I did last time. I'm going to hit the alpha key, then the y equals key. So I do a nice up and down fraction. If you don't do this, make sure you use parentheses in the denominator. 23 divided by pi r squared, or pi x squared in this case. And then the square key. Let's see.
Don't we have to store
No, we don't have to store this one, because.
3.08?
So what interesting thing did you see when you pressed the enter key?
Same number.
Yeah, it's the exact same number. So what that's saying is that this can has the same width as it does height. In other words, if you look at it in profile, it looks like a square. And in fact, years ago, I had this really cool neighbor. He was a World War II veteran, and he built me that can out of wood. And according to local legend, he says that it was accurate to within 1/10,000th of an inch. I don't know. I think he's off a little bit. Just kidding. No, it was really cool. But I'll pass it around. So this is that can built to those dimensions.
How many ounces does it hold?
It holds exactly 23 ounces, which leaves enough room for 12 fluid ounces and then a little bit of space for air. So it's pretty cool. Now, the big question is, well why don't people make cans like that? And the answer is several-fold. First of all, as that can comes around, you notice that it's not exactly very comfortable to hold in your hand. So consumer preference plays a big part in this. And the other answer to the concern of reducing the amount of aluminum, there's been a lot of changes in the production of these cans. It used to take about 36 pounds for 1,000 cans. They've gotten that down to about 32 or 33 pounds. And then lastly, the best answer to these environmental concerns is to recycle. All right? Aluminum is very intense in terms of requiring a lot of electricity to make it, and you save about 90% of that energy by recycling. So it's a good thing to recycle. So cool. All right, Comments or thoughts on our super can here? That was kind of cool. Was anyone else surprised by the result that the dimensions were kind of the same? I thought that was kind of interesting. If you look on the shelves of some of the items you'll see in the grocery store, cans of Fresh Like corn have that same kind of profile. That is, their height and their width are the same. They kind of look a little boxy if you look at them from a little bit of a distance. So you will see manufacturers adhering to that here and there. It's kind of cool when they do. Now you do have a test next week. I want to take a little time and go over with you last year's test or last summer's test and talk about some of the ideas behind some of the problems here, some of the things that I expect. So let's see. Here's one from section 4.9. Your test is going to cover, I think, 4.1 to 4.9. So it's going to start with the material we started with after the break. You should be able to do the mean value theorem. So I would definitely practice that. This one, it's a nice polynomial function. It's basically just asking you, does it satisfy the mean value theorem? If so, find that point. Make sure you work in the interval -1 to 2. What is the mean value theorem saying anyways? What's the mean value theorem say? I drew in this interesting line here. What's the mean value theorem say? All right, it is continuous from -1 to 2. It's continuous.
It's differentiable on -1
It's,
to 2?
yep, it's differentiable on -1 to 2. So when you're meeting the conditions for the mean value theorem, it says basically that there's some point between -1 and 2 where the slope of the tangent line is going to match the slope of the secant line, which is what I have here. So some point probably around here, when you differentiate that, you're going to see the slope of the secant line matched by the slope of the tangent line. What tells you the slope of the tangent line? Derivative. How do you find the slope of the secant line? You seek it out. If you seek a beautiful peninsula, look about you. Does anyone recognize that? Yeah. So what you need to do basically is just find the slope of a line between those 2 points. Just do a little t-table here. Nothing big. Find the slope of the line. Set the derivative equal to that slope, and bam. Let's keep going. Just some basic increasing, decreasing, concave up, concave down stuff. A nice polynomial. That's bread and butter stuff. You should be able to nail this one. This one is a gift. It's like a nice polynomial, not any trig functions or exponential functions. You don't have to use a chain rule. You should be able to tell me where it's increasing, decreasing, concave up, concave down, local mins, local max. We kind of mentioned this one today here a little bit. G of x is a continuous function on this interval, -3 to 7. Suppose that g prime of 3 was equal to 0, but g double prime of 3 was equal to 12. What's that telling you about this function? What do you know now?
It's a minimum.
It's a minimum. Good. Why is it a minimum?
It's concave up.
Yeah. This first little bit tells you that the function has a critical point here. The second bit says that it's concave up there. If you have concave up shape where you have a minimum, okay, or where you have a critical point, then it's a minimum. And then obviously the reverse situation down here, what can you say about the point at -2? Maximum. All right. We spent some time working on problem just like this in our homework when we covered section 4.6, I think it was. Basically, you're going to need to find with your calculator where the function is increasing, decreasing, concave up, and concave down. I'll give you a drawing of this. But what are you going to have to do to find out some of this information? That is, for instance, where it's increasing, where it's decreasing, concave up, and concave down. How are you going to figure that out? Yeah, you have to use your calculator, right? So let's remind ourselves how to put something like this in. Now, for this one, I think you can differentiate this without being really fancy, right? let's put that into our calculator real quick and remind ourselves of a few things. So I want e to the x minus, and what was it?
0.6.
0.6x squared. Yeah. 0.6
It's x cubed.
to x cubed. Thank you. X cubed. Bam. Now you've got a couple things you can do here. You can put in, depending on the function and how ugly it is, you could, in this case, easily calculate the derivative. What's the derivative going to look like in this one? Iris? What's that derivative going to look like? E to the x. Good. Minus 1.8 x squared. Thank you. All right, so there's the first derivative. Now I'm eventually going to need the second derivative, right? I want to look at both of these things. Let me remind you that you can do some of these things numerically. So do you remember where to find those things numerically? You're going to go to the math menu. So if I want the second derivative, it's enough just to differentiate the first derivative. So go to the math menu, option 8, d by dx of, let's see, I want y2 here. So you can find y2 with the vars menu, over to yvars, function, y2. So it's going to differentiate that with respect to x. So put in that extra x there. Great. Now if I want to find where the second derivative is 0 and or changes sign, then I can look at its graph. I'm going to shut off the graph of these other two. You do that by pressing the enter key on the equal signs for both of those graphs. And now it's not going to graph either y1 nor y2. As far as where to see this graph, if you don't know much to begin with, then one thing you can do is just do kind of a shotgun approach. Zoom 6 gives you the standard window, -10 to 10. And that should give us a good place to start. You can zoom in on this graph pretty easily if you want. You can just change the window sizes, or zoom box is kind of a cool trick. Hit zoom box and then move the cursor around to find what you want to be in your new viewing window. When you find one corner of that viewing window, press enter and then move down, stretch out the other dimension of your viewing window, and then when you get it all set, press enter. That'll be your new viewing window. So there we go. Then you can use this to figure out, well, where does this graph cross the x-axis? You need to find both of those 2 points. You can do that from the calculate menu. Second, calculate. I want to find the zeros there. So let's find the 0 for this one. Go to the left of your 0, press enter. Go to the right of your 0 and press enter twice. That's the root. So you need to do that a couple times to find both roots, but overall it's not too onerous of a problem. Once you have that, do you have to test points? Not really. You could, but this goes from positive to negative to positive. So you can see what happens with the second derivative there. So you get a little break in terms of the work that way. L'Hopital's rule. So you should expect a little bit of work with some trig functions. I hope you haven't forgotten their derivatives. How do you know you'd want to use L'Hopital's rule in something like this?
0 x2 like 0 or infinity.
Yeah, you're either going to have 0 over 0 or infinity over infinity, infinity over negative infinity, or some combination thereof. But you can have an indeterminate form. Be careful when you differentiate the sign in the denominator. You've got to use the chain rule. Not only are you differentiating the sign, that's the derivative of the outside, times the derivative of the inside is going to give you a 2. You have to use a chain rule there. For this one, once you apply L'Hopital's rule, you're going to look at it and go, oh, I still have 0 over 0. So you have to apply L'Hopital's rule again. You might have to apply it a couple times. And finally, this one down here, a little bit more difficult. Let me just kind of show you what goes on with that one. When you try and evaluate the limit, essentially what you get is 1 to the infinity power, which doesn't really work, nor is it in the form of L'Hopital's rule. So the trick there that I talked about in my video was take logs on both sides. And you use the properties of logs. That 1 over x term can be taken out in front because of the properties of logarithms. And then I'll rewrite it like this. ln of 1 plus 3x over x. And now this finally satisfies L'Hopital's rule. If you differentiate the numerator divided by the derivative of the denominator, you get this. So you apply L'Hopital's rule, you finally get a limit of 3. But keep in mind, that just tells you the log of your limit. To unlog both sides, you're going to exponentiate both sides, and overall your limit's going to be y equals e to the 3rd power. I'm not sure what I did here. Yeah. Quick question here for you. How can I verify that I did my calculations right? When I look at that limit, I'm like, how do I know I got it right?
Take your derivative of
Just plug it in.
Plug it in where?
Wherever
Initially.
How could I verify I got it right?
Can you graph it?
Yeah, let's graph it. So let's graph 1 plus 3 to the x, or 1 plus 3x to the 1 over x power. So let me just get a new one here. Y equals 1 plus 3x raised to the 1 over x power. And let me move this down a little bit. So it does cross the y-axis at some point. Let's see if we can't estimate what that point is. Now it's actually not defined right at 0. And you can see it when I hit it just right, it's undefined there. But it certainly looks like it's pretty close to 0 and e to the 3rd. How about e to the 3rd? Yeah, looks pretty good. So we feel pretty comfortable in our answer. Yes, ma'am.
Let's say for some reason our graphing calculator dies and runs away and there's none left on Earth. Could we possibly set it equal to, like set the original function equal to e to the 3rd? Would we be able to check that way or no?
But you still have to calculate the limit.
There's no way
I mean,
to check the
other-
limit with that calculator?
those are the two ways that would come to my mind first. One is you could actually, let's see, you could plug in the function into your calculator. Let me clear out this stuff. 1 plus 3x raised to the 1 divided by x. Now we already looked at it with the graph, but there is actually another way that you can use your calculator to look at it and try and decide if you got the right thing. Let's compare our answer to e to the 3rd. So that's just a constant function. But what you could do is look at the table and get closer and closer. You can start with like 0.5, 0.1, 0.001, etc. And what you'll see eventually is that it's going to get pretty close to the limit. So 0.1, 2, 3, 4, one extra one won't hurt. So there you go. As far as being able to check it without a calculator, yeah, I can't think of anything off the top of my head. Yeah, but there's two ways you can check it with a calculator. Okay, what else do we have on last year's exam? Your vertical asymptotes. Vertical asymptotes of a function are going to be where what happens? How can you find the vertical asymptotes of a function?
The roots of the denominator?
Yeah, roots of the denominator. Now in this particular case, I think there's a little bit more going on than just finding the roots of the denominator. If you factor this, notice that that x minus 1 term cancels out from both the numerator and denominator. that's going to be where you have a hole in the graph. And you can find the coordinates of that hole by calculating the limit. Limit as x approaches 1. You know, essentially you don't need to use L'Hopital's rule here. You can just use this kind of abbreviated version of the function x over 1 minus 3, and you get the point, the hole in the graph is 1 and negative 1/2. As far as the horizontal asymptotes are concerned, that's going to be when you take the limit as x approaches infinity. Where does this graph go as x approaches infinity? In that case, that limit is going to be y equals 1. So you can find a couple different asymptotes using limits. Your horizontal asymptotes are what's going to happen as x approaches infinity. Vertical asymptotes are going to be where the denominator is 0. And then finally, we've used a limit to find the hole in the graph. So a couple possibilities for us there. We did this one already this morning. Here's another one that we did the other day. The cutesy trick here was in coming up with a function that instead of minimizing the function, the distance, we squared it. And getting the minimum of d of x and the minimum of s of x are going to be the same. It's just easier to work with s of x. We just finished that one. And then some antiderivatives. All right, that's going to be where your function or where your exam ends. So everything that has a derivative rule in it is now going to have an antiderivative rule. So what do you differentiate to get the secant squared? Oh, the tangent. What do you differentiate to get the cosine? The sine. Unfortunately, it's not quite a reciprocal relationship. If I differentiated something to get the sine, what did I start out with if I differentiated something to get the sine? Negative cosine. Yeah, spot on. Couple tricks along the way here. This one's a good one that I'd be on the lookout for. That is, if you have something like this, it's a quotient, you can't find the antiderivative of the numerator and divide it by the antiderivative of the denominator. It just doesn't work. What you have to do is you have to divide each term in the numerator by that term in the denominator, and then find its antiderivative. What's one thing all of these have that you don't want to forget because you'll lose a point? Plus c. Absolutely. Yeah. And then the antiderivative of 1 over x is log of x. So, nice. All right. I think that gives you a rundown on pretty much the things I expect. Comments or questions on any of these things?
Yes.
Yes.
Do we have to follow the steps where it's like picture, interval?
So when I grade your papers, a lot of times, especially if the problems are a little bit more involved, what I'll do is I'll allocate certain amounts of points for each step. So picture would be worth 2, function might be worth 4, interval might be worth 2, analysis might be worth another 4. So I'm going to be looking for those steps along the way. And if your work matches those steps, it helps me and it helps you. So I would encourage you to use it. Do you have to follow it exactly? No, but I encourage you. All right. Anything else? Lucas? Look good?
I'm good.
All right. Cool. Let's